We all have heard about ray tracing, but today I'm gonna talk about how it works and its basics. Ray tracing rays are casted to simulate real life lighting, and when we say shooting out rays, we think about something like this. But it wastes a lot of computing power. We can just do this and call it a day, right? So, well, what's the solution, you ask? Well, it is that we have to shoot the rays from the camera. I wish I was joking. Okay, so here's our plan. We will shoot the rays from our camera, and when it will hit something, it will send a ray to the direction of the light source. We can calculate how much light from the sources will be reflected, which is called direct illumination, but also how much light from the surrounding objects will be reflected, which is called indirect illumination, which is the trickiest part, but it's needed for global illumination. Here is an example of global illumination that I sketched on my script. And I'm not good at drawing, so don't judge my drawing skills. To compute direct lighting for a pixel that finds the closest intersection between the camera array and our scene, the direction of the ray is the direction the camera faces. Offsets can be made according to the pixel's screen coordinates. Pixels that are directly in the center will shoot straight rays, while pixels on the side of the camera will shoot at angles. The stronger the divergence, the wider the FOV. After a hit has been detected, an array is cast to the light source. If the ray is blocked, the pixel doesn't receive any direct light, which causes a shadow. If the light isn't blocked, however, we need to compute how much light from the source will be reflected to the camera. We can estimate this using the equation below. Okay, fine, that looks too hard. I'm gonna give you a visual representation. I hope this makes it easier to understand. Also, when I say multiplying a color, I just mean multiplying the RGB values with each other, which only makes sense when these values range from 0 to 1 and not 0 to 255. For example, look at this. But the shadows end very abruptly, which makes it look fake, and so I won't stand for it, as real life shadows are smoother. This is because light sources don't just emit from a single point. Areas near a shadow can therefore receive a small part of the light that isn't completely blocked, which is called the penumbra. We can simulate this effect by giving the light source a radius and casting many rays to different points on the light sphere. The portion of rays that successfully reach the light is then used to calculate the received illumination. The idea for indirect lighting is very simple as well. For every point the camera array touches, we can cast a bunch of rays in surrounding directions and treat every point we hit as its own light source, emitting the light it receives back but multiplied by its albedo. The complicated part is figuring out how much light from these points will be reflected by the inertial surface back to the camera, and we have to take the surface's roughness values into account. Roughness is a material property that determines how much light gets scattered. A roughness of 0 means 100% of the light gets reflected into one direction, like a mirror. Then there's progressive rendering. The idea for progressive rendering is that instead of rendering every frame from scratch, we reuse some parts of the old frame and we use it in the new one. The most recognizable feature of ray tracing is reflections. If you think about it, ray tracing is just a form of indirect illumination. Just instead of sampling in random directions, you sample along the reflected direction or randomly in a cone around the reflected region to get blurry reflections, and this is once again related to the surface roughness. If it is 1, we sample it in all directions, and if it's 0, we only sample in reflected direction. But sometimes we get this unrealistic jagged edges called aliasing, and it happens because all arrays for a single pixel are always cast in the exact same direction, which means that the pixel's color is entirely determined by a single point in the scene. To smooth out our edges, we should base a pixel's color on multiple points lying inside it. A simple way to do this is without sacrificing frame rate is to take advantage of our progressive renderer pipeline and simply add a slight random offset. If the offset is too much, we get a blurry mess, so we need to make sure not to make that offset too big. Anyways, that's gonna be it for today, and subscribe for more low quality videos.